This is lecture 4, and this is the first of, I think, 5 lectures. I divided them up, and so I kept the first page for all of them. Lots of new stuff where it's essentially the introduction to RISC-V, and then followed by a new experiment. So RISC-V, remember, it's a type of computer, or we'll call it a microcontroller, which is typically what I call it. It's a device that reads instructions from memory and executes them. So the RISC-V Otter is it's kind of a really interesting thing. It's open source, and the idea of this thing was it was defined strictly by an instruction set. So someone plopped an instruction set out there and said, okay, we'll make it into a computer. The idea of the hardware that supports it was kind of anyone's creation, and this was, like I said before, this was created by Joseph Kayena Sloan in the EE department. So this instruction set is purposely made to be generic as possible, so you can solve many different types of problems, and that's the general approach. So this is an assembly language program, and essentially it actually does something, and it doesn't really matter what it does here, but we've talked about this before, but now we need to delve back into it. So there's 3 parts of this program. There's directives, comments, and instructions. So let's look at this. Look at the comments first. So these are the comment characters. It's a £, anything following a £, is ignored by the assembler, which essentially makes it a comment. And so I've got comments in the first column. Over here I have comments in some other column. Next thing we want to look at is, comments in general, they're a message from one human to another human. It's like from a programmer to another programmer. Next thing we have is these directives here. This is an assembler directive. You don't need to know exactly what this does right now. We'll talk about that later, but this is a message from the programmer to the assembler. So the programmer has somewhat control over the assembler. One way it controls the assembler is by issuing or writing these assembler directives. And once again, we'll talk about that later. Next thing we have here is the actual instructions. These are the actual instructions. That's all you get. You have to put those down as written as they're written there. Nothing else, and that way it interprets it as an instruction. These are the mnemonics. These are the operands, so we'll get into that later. And as you can see, they have specific or different types of operands and different number of operands. For example, this has 3 operands. This has 1 operand. That has 2 operands. So lastly, and I still don't know how to classify this, is the notion of labels. So these are labels. These are 2 labels here, and they're actually potentially very important for the circuit. They help the assembler do its job, but they also kind of can be used as comments, and so we'll get into that more later. For example, this label here is a comment. This label here, it's actually used in the instructions. So this is actually a jump instruction. It's jumping to the instructions associated with the main label. This label is never used, though it means something to human. Obviously, it means like some type of initialization code, and we'll get into that later. But once again, I'm not sure what they are, whether they're comments or instructions or directives. Certainly, they don't increase the length of your program. So they're always a good idea to use. So the instructions themselves, I think they break down into 2 categories. They either do something, or kind of what the whole point of this lecture is today, they tell the microcontroller to go somewhere else and do something, which is essentially branch instructions or jump instructions. We'll get more into that later. In terms of the underlying hardware, these instructions either use this block, they crunch bits, they pass data back and forth between these 2 blocks, and otherwise they just tell the controller or the the program to go somewhere else and do something. That's all instructions do. They're actually very simple, as you'll see as we get into them. So this is actually very important. So when we're talking about RISC-V instructions, there's two types of instructions. There's these ABI instructions, and I think that means application binary interface, which I'm not really sure exactly what that means, but I call them base. They're better known as base instructions. And that's essentially, these are the instructions that are supported by the hardware, but there's also quite a list of pseudo instructions. So the pseudo instructions are not real instructions. Essentially, when you put a pseudo instruction down there, the assembler converts them into a base instruction. So we'll get into more of that later, but once again, there's two types of instructions. There's real instructions or base instructions, and there's also pseudo instructions. So once again, this is breaking these instructions down. They tell you to go somewhere, they crunch bits, they transfer data back and forth between memory, and then there's a few extra auxiliary instructions that we'll talk about later also. So these are example of a couple instructions. You of course don't need to know what they do, but they have kind of a generic format on these things. So these are the actual instruction mnemonics. Each of these mnemonics have a number of operands following it. So this the example of 0, 1, 2, and 3 operands following it. And you don't need, once again, you don't need to know exactly what this is doing, but what you need to know is the instructions have operands, and that tells the instruction what it's going to be doing. So there's a particular type of vernacular, or not vernacular, but format these instructions use. Essentially, it uses this RD to mean the destination register, and this RS to mean a source register. So that essentially, it's something we'll get into later. Essentially, these are two source operands here, and what this instruction is going to do is add these two source operands and store the result in that destination operand. So the destination is always where the result of the instruction, the operation in that instruction goes. Typically, this X means here, it can be any register. Typically, you can use any of these registers as a source. Actually, shouldn't have put an X0 there, because as you'll see, X0 is not writable. X0 is a register that always has a value of 0 associated with it. So that means you can't write it, but you can actually read the thing. You can use it as a source, which you'll see later. So there's 3 levels of instructions. You know, when you issue an instruction in a higher level language, it looks sort of like that, but the compiler is going to break it down into these lower levels here. So particularly if you issue an instruction like this, it's going to break it down into maybe an add instruction that looks like that. Now here, this is just something that's comfortable for us humans to read. Essentially, the computer only understands binary, or essentially bits. So the instruction is going to break it down in something that looks like that. So every instruction is 32 bits. That's really impossible to read. Typically, we'll be working with hex on this thing, but every instruction is associated with 32 bits underneath it. So these are the instruction formats. They're 32 bits, but it's actually in a very well structured format, and you'll see that as we go along. There's actually 6 different types of instruction formats. There's actually more than that, but we just call it 6. Here is an R-type format, and so what that means is this R-type format supports this add instruction right here, and the idea here is this add instruction has 2 types of fields in it. It has opcode fields, so these are the 3 opcode fields, and it also has some field codes. So these are the 3 field codes right there. Now the issue is that these opcodes are constant for the instruction. The assembler uses these opcode fields to determine which instruction you're executing. These field codes are associated with registers. These field codes are anyway. If you notice, we have 32 registers. That requires us to use 5 bits to differentiate those registers. Those are the 5 bits right there, these 5-bit fields. So it's not coincidental that we need 5 bits to differentiate 32 different things. It's just straight binary. There are, once again, I think there's 7 different instruction types that we kind of just talk about them as 6. Here are the 6 instruction types. What I want you to take away from this is pulled out of one of the manuals. What I want you to take away from this is these fields are kind of lined up as best they can line them up, as you can see here. And that's done purposely for reasons we'll get in later. It just simplifies everything. You can see these are lined up and these are lined up too as best they can. We try to line everything up. And like I said, it simplifies the hardware, simplifies the implementation. And essentially, I think that is it for this slide. This is just our high-level diagram once again.